what is continuity? So continuity is where you can take your pen or pencil, put it on the paper, and draw a complete line with no breaks in between. Now let's go ahead and actually prove if this is continuous or not. So let's choose a point and we'll just call this 3 and we'll use that right there. Now we're going to be going over limits to define if it's continuous. So there's 3 steps. Step number 1 is to see if f of 3 exists. And let's just give that a point of 3 also. So step 1 is true. At the function f of x equals 3, it is defined. Now the second step is to see if the left and the right limits are the same. So what does that mean? Let's write that down. The limit when x approaches 3 from the left. So what this means is this is the negative side and this is the positive side. So when x is approaching 3 from the negative side, it's going from this side all the way to this line. And when it goes that way, it's 3. So limit of f of x when x is approaching 3 from the negative side equals 3. Now we can also do the same for this, except we can write that as positive. So limit of x approaches 3 from the positive side, and we denote that with a little plus sign here, of f of x equals, and that's from the positive side coming all the way here to 3. And that's also at the value of 3. So now that we have the left and the right limits are the same, and it's defined at this point, we can go to our third step. And our third step is setting these values equal to each other. Now, since the left and the right limit are the same, we can now write the limit plainly at x equals 3 of f of x equals 3. Now, I didn't put a minus sign or a plus sign here. That's because the left and the right limit are the same, and because they're the same, I can write this equal to 3. Now, if the left and the right limit were not the same, I couldn't even write this. And now we just put f of 3. And that's it. So what we did here is we first compared if the point at here itself exists at f of 3. And since it does, we can go to our second step. Our second step compares the left and the right limits. For this one, we looked at going from the negative side to 3. And that's what that little minus sign here means. And that equals 3. Also, coming from the positive side here, all the way here, also equals 3. And then our third step takes, well, since these two are the same, we can just write the x, limit of x approaching 3 equals 3, and that's also equal to f of 3. So since they're all the same, this is continuous. Now we have a different function here. So in this graph, all of the points are actually defined, like they all have a point at the value itself, except for here, where there's a jump, it jumps up. This doesn't have a value, but this up here does. So let's see how this works. So let's prove if this is continuous. Step number 1 is to see if I'll name this g of x. If the function g of x at x equals 4 has a point. So we can write that as g of 4 equals, and we can see g of 4 equals 6. Now we don't want to use this open circle because that means that doesn't exist. This closed circle is the part where it does exist. So when we get g of 4 equals 6, and that's right here. Now our second step is to see if the left and the right limit are the same. So we go ahead and do limit of g of x as x approaches 4 from the negative side, and that's from this side going this way. And from this side we can see we can follow this function here. So as we follow this function, we see right there, that's where it equals from the negative side. So that's 5. And we can also do the same for the positive side. And for the positive side, that's from this side coming this way. So going this way. And we can follow this function up here to see where that goes. And we follow it, and we see it goes to 6. Now, the left and the right limit are not the same. This is 5 and 6. 5 does not equal 6. So that means we cannot write this limit. This is not a thing. The limit of g of x as x approaches 4, just in general, not from the left to right, but just in general, because the left and the right limit are not the same. So when we go to our third step of proving if it's continuous, we see that this equals does not exist, d and e. And since this does not exist, well, does not exist does not equal 6, which we got up here. And also, does not exist if you run into this, does not equal d and e also. So since we got d and e, that just proves that the third step has failed, and this function is not continuous. But that goes into different types of discontinuity. Now we're going to be going over different types of discontinuity. And the first one we'll be covering is the whole discontinuity. So here's an example of a whole discontinuity at x equals 2 and at x equals 8. Right here is an example of a whole. Even though it literally has a hole here, it still can have a value defined at x equals 8, which is also 8 for the y value. Here, it can also not have a defined value, so it doesn't have to have another value up here, down here. It can just be a hole. So how might we run into a whole discontinuity? And that's the example here. So we have our function x minus 3 over 4x squared plus 15x plus 9. And when we factor it, we get x minus 3, 4x minus 3, x over x minus 3. And so we can go ahead and cancel these, and then we're left with 4x minus 3. Now this is a simple y equals mx plus b type equation that we can easily graph. But at x equals 3, and how do we get that? Well, we can just take the function, the polynomial be removed, which is x minus 3 equals 0, and we get x equals 3. And so at x equals 3, there's going to be a hole. So 4x minus 3 is going to look roughly like this. But at x equals 3, we're not going to have a point there. Instead, we're going to have a hole there. And so that's how you're going to get a whole discontinuity. So for the whole discontinuity, you could pass the first step of continuity test, which is the first step. So I'm going to use x equals 8 as an example. So for f of 8, we also get 8. And for the left and right limit, you're going to get 7. So for the second test of continuity, the limit as x approaches 8 from the negative side of f of x equals, and that's an equals 7, which is right here. It's not going to equal this value up here because the function converges at this point right here. That's where the limit goes. So equals 7 equals also the limit from x approaching 8 from the positive side. But it fails at the third step. The third step is where we compare f of 8 does not equal the limit of f of x as x approaches 8. Not from the left or right side, just as x approaches 8. Because this will get you 7, and this will get you 8. And 7 and 8 are not equal. Now, if we want to test x equals 2, which is right here, well, it's going to fail the first one. So since it fails the first step of proving if it's continuous, you can just stop right there and it's discontinuous at x equals 2. And the type of discontinuity at x equals 2 and the type of discontinuity at x equals 8 is a whole discontinuity. Now another type of discontinuity in this example is at x equals 5. So this is not a whole discontinuity since the left and right limits are the same. This is a jump discontinuity because it literally just goes ahead and jumps by a lot. It can either be a jump up or a jump down. So let's test it to see what the difference here is. So let's go ahead and use our first step of proving if it's continuous or not, which is f at 5 equals 1. And so at f of 5, we're using this value here because it is filled in. We're not using this one because it's a circle, meaning it doesn't include that point. So at f of 5, it's 1. Now we go to our second step. The limit of f of x as x approaches 5 from the negative side. So that's from this way going this way. And as we follow this function, we see that's going to equal 1. Now we can test from the right side. So limit as x approaches 5 from the positive side of f of x equals, and we go from this way, and as we follow this function here, we get 7. So now we can see the left and the right limit are not the same. So when we go ahead and use our third step, which is f of 5 equals, well, it doesn't equal that because the limit of f of x as x approaches 5, not from the left or right, but just as x approaches 5, equals does not exist. And when you get does not exist, you can just stop right there, and it fails the third step, meaning it's not continuous at x equals 5. And the type of discontinuity is a jump discontinuity because it literally just jumps, and it can be a jump up or down. And the last type of discontinuity is called the infinite discontinuity, and that's when we have an asymptote. So at x equals 9, well, it doesn't really ever equal x equals 9. There's no value because it infinitely gets closer and closer but never actually reaches. And we can show that by it increasing without bounds very quickly. So it's going to reach very, very high numbers. And here's going to reach very, very low numbers, but it never actually gets to x equals 9 because it's either increasing to negative infinity or infinity. So we can see this when we prove continuity. So our first step is to see f of x at x equals 9, but it never actually equals this. So we can actually just stop right here because we got does not exist, and this is discontinuous. But let's continue. So the second step is the limit as x approaches 9 from the positive side of f of x, and that's from this side going this way. And so we follow this function, and it decreases without bounds. So it's just going to negative infinity, and that's the function behavior because it goes very, very small in terms of numbers. And same thing for the limit of f of x as x approaches 9 from the negative side now, and that's from this side going this way. We can follow this function up, and it's increasing without bounds. It's just the function behavior is infinity. It's getting really high for its numbers. And so when we go to our third step, it's when we do f of 9, this does not exist. The last part cut out, so I'll continue from step 3. For step 3, f of 9 equals does not exist, and that is not equal to the limit of x going to 9. Again, not the limit of x going to 9 from the negative or positive side, just the limit of x going to 9, and that's because the left limit and the right limit were not the same. And that also equals does not exist. So these are not equal, and the third step proves that it's discontinuous. And by the way, does not equal does not exist. So we have a practice problem here. So let's find all about this function. So we can simplify this to x minus 2 over x plus 2, x minus 2. Now, we can remove this part, and we simply just get 1 over x plus 2. Now, this has a removable discontinuity at x equals 2, and we can just use this, x minus 2 equals 0, x equals 2, and we remove this entire polynomial from the function, so that means it's a removable discontinuity at x equals 2. Now, also at x equals negative 2, there will be a hole, because when we do x equals negative 2, it does not exist. So this function is discontinuous at x equals 2 and at x equals negative 2. So there's 2 points of discontinuity. This one is a removable discontinuity, this is a hole. Alright, let's see if this function is continuous. Now this function has 2 functions within it. We'll just call this the first subfunction and the second subfunction. So let's prove if it's continuous. Now, the way we prove if these types of functions are continuous is we take these values they give us and we just directly plug it back in. Now, if it's a polynomial that we can simplify, like the last example, we go ahead and do that first. But since I can't do that here, let's just directly plug 0 in. So cosine 0 plus 1. This will give us 1 plus 1 because cosine of 0 is 1, and this gives us 2. Now, we have 2 minus 3 times 0. And that also gives us 2. So what this means is the left and the right limit are the same. Now, we can see this function is true if x is greater than 0. So that means this is to be the right limit of the function. And this is true if x is less than or equal to 0. And this will be the left limit of the function. So we can write this as the limit as f of x with x approaching 0 from the negative side, and we'll get this function, this equation is the same as the limit of f of x as x approaches 0 from the positive side, and that's equal to 2. And so this function is continuous at 0 because the left and the right limit are the same, and since the left and the right limit are the same, we can go ahead and we can write this. The limit of f of x at x is approaching 0, not from the left right, but just as x approaching 0, equals 2. And that's how we get this function is continuous. Now for our last example, which will be somewhere on screen, well, it looks like a mess of a function, but let's go ahead and quickly walk through all the types of discontinuity. So this function is continuous for all of x except for the following. At x equals negative 2, there is an infinite discontinuity because the left and the right limit increase without bounds. At x equals 2, there is a jump discontinuity because it jumps downwards as you continue from left to right of the function. It is defined at the point at x equals 4. When x equals 2, y is 4, but it is a jump discontinuity because it jumps, there's a gap right there, and the left and the right limit are not the same. At x equals 5, there's another infinite discontinuity. That's because the left limit increases without bounds and the right limit decreases without bounds. So the left and the right limits will not be the same. At x equals 6, there's another jump discontinuity. At x equals 8, there's a hole, there's a removable discontinuity. At x equals 10, there's another removable discontinuity, which is a hole. And at x equals 11, there's a jump discontinuity.